This is our presentation on prominent forms of solar activity. To start, we're going to discuss how solar activity even occurs. It's believed that solar activity occurs due to the magnetic field of the sun. The magnetic field of the sun is so massive that it causes energy to be released in massive forms of radiation that are shot out into space. This can cause many forms of solar activity, but the ones we are going to discuss are solar flares, coronal mass ejections, sunspots, and solar wind. We are first going to discuss a solar flare. This happens on the surface of the sun, where sudden bursts of radiation cause massive amounts of photons to be ejected into space. Solar flares generally are a catalyst and give way to a coronal mass ejection. A coronal mass ejection, or CME for short, is a more violent explosion of plasma and magnetic field that scatters billions of tons of matter into space. In our image, you can see by all the streaks in this blue image and this orange one that are happening above the body of the sun. The next form of activity we're going to talk about is a solar wind. It's very similar to wind on Earth, however, it is much, much weaker. Solar wind is also caused by the outward expansion of plasma. The final form of solar activity we're going to talk about is a sunspot. A sunspot occurs when the magnetic field is slightly emerging through the surface of the sun. Since the magnetic field is emerging on the surface of the sun, this allows a part or spot of the sun's surface to temporarily cool. Because it is temporary cooling, we see a large dark circle forming, as you can see in this image.
Hello, my name is Michael Martinez, and I'm going to be discussing how does solar activity reach Earth and what effects it has on the Earth. So I'm mainly going to be focusing on 4 forms of solar activity, the first one being solar flares. So for solar flares to actually reach the Earth, the side of the sun where they occur on must be facing the Earth, as solar flares are made of photons that travel directly outwards from that site. So a rule of thumb that we can follow is that if we are able to see the event occur, then that means we can also be affected by it. For coronal mass ejections, otherwise known as CMEs, to reach the Earth, the cloud formed from the explosion must be aimed at the Earth. For solar wind streams, these streams are formed from coronal holes, so if the holes that they occur at are closer to the solar equator, that means the wind stream itself will actually reach the Earth. For solar energetic particles, when these are released, they follow magnetic field lines outwards into our solar system. So they actually only reach the Earth if the magnetic field line that it follows intersects the Earth. So for the effects of solar activity on the Earth, we mainly see 3 main forms of effects, from environmental and climate to technological to physical human effects. For environmental and climate effects, solar activity has actually only contributed about 10% of global warming between the mid-19th and the mid-20th century. After the mid-20th century, we have seen that almost all global warming that has occurred has mainly been caused by greenhouse gas emissions from humans. For the technological effects of solar activity, we see that they have disrupted electrical power grids, and they can even corrode oil and gas pipelines. When they occur, they interfere with our radio communications and even our GPS navigation. For spacecraft that are in space during a solar event, the spacecraft itself can have the electronics damaged and the imagers used blinded. For physical human effects, for humans on Earth, we really don't have to worry as we are protected by our atmosphere and the magnetosphere. But for astronauts that are in space, they can, if they are in space during a solar event, they can easily reach a radiation exposure limit within hours of the event. Some famous examples of solar events that have affected things here on Earth are during 1859, during a solar event, the telegraph service was disrupted. During 1972, the Apollo and 17 missions, there was a large solar energetic particle event that threatened the lives of the astronauts during the mission. In 1989, during a series of geomagnetic currents, the Hydro-Quebec power network actually collapsed from these events.
After talking about forms of solar activity and how it affects Earth, we can also look at how it affects climate change. The energy that warms the Earth's atmosphere comes from the sun. which is referred to as visible light. When visible light reaches Earth, some of it gets reflected back into space by the atmosphere, but most of it passes through the atmosphere and gets absorbed by Earth's surface. The surface gets heated and emits thermal radiation in infrared. As the infrared is trying to return to space, a layer of greenhouse gases absorb and re-emit infrared radiation, and result heats the lower atmosphere. This process is called the greenhouse effect. This process is similar to a blanket keeping our body warm. The greenhouse gases, or the blanket, doesn't produce heat, but it rather traps the heat within the respective containers. The greenhouse gases are carbon dioxide, methane, nitrous oxide, and water vapor. They are produced naturally by our atmosphere, but are also man-made by humans. On the next slide, we can see that humans add excessive amounts of greenhouse gases to the atmosphere by burning fossil fuels. From 1990 to 2014, human emission of CO2 has increased by 9%. According to the EPA, 50 to 65% of methane is human produced. As we can see in the graph below, we can see how much each human-caused greenhouse gas contributes to total emissions around the globe, and then their respective global warming potential, or GWP. The more greenhouse gases that are in the atmosphere, the greater the warming of the greenhouse effect is. According to NASA, since 1750, the warming driven by greenhouse gases from humans burning fossil fuels is over 50 times greater than the extra warming coming from the sun in that same time period.
The effects of solar activity from our sun are felt throughout the solar system. For example, during a solar flare, ultraviolet radiation from the sun strikes Venus' day side and ionizes the planet's upper atmosphere. This forms a plasma that makes up the outermost layer of the atmosphere, the ionosphere. Venus doesn't have its own magnetic field due to its slow rotation, but when the thermal pressure of Venus' ionosphere pushes back against the magnetic pressure of solar wind from the sun, it creates an induced magnetosphere. As solar wind strikes a planet, it forms a standing wave of plasma that slows down, heats, and deflects the flow around the planet, called a bow shock. Where this bow shock lies above the surface of a planet affects the planet's climate. Venus does not exhibit a magnetic field, therefore its bow shock is just 1,000 kilometers above the planet, only held off by the ionosphere. This closeness of the bow shock to the surface leads to intense interactions between solar wind and Venus' atmosphere. The ionosphere lies at a much lower altitude on the day side of Venus than on the night side because of the pressure from solar wind. Venus's interaction with solar wind also result in continuous loss of hydrogen and oxygen from the planet's upper ionosphere into space. A common hypothesis to why Mars had an active hydrological cycle 3 to 4 billion years ago, but does not today, is that solar wind eroded the Martian atmosphere, intensifying the greenhouse effect and causing the hydrological cycle to collapse. Unlike Earth, Mars has no magnetic dipole. The solar wind instead induces currents in the ionosphere, creating an induced magnetosphere and causing ion escape. Solar flares also more dramatically affect Mars than Earth. Solar flares cause up to 200% enhancement into the ionosphere of Mars, which is the influx of solar photons causing ionization. During a flare, Mars's atmosphere heats unevenly, and in the hottest parts of the thermosphere and ionosphere, they interact with each other. Molecular oxygen then escapes to space at a much higher rate than on Earth. Saturn and Jupiter have well-developed magnetic fields like Earth, and are therefore much less affected by solar wind than planets like Venus or Mars.